Hi everyone, Vadim here from LangChain. Today I'd like to show you how to build and deploy a self-corrective RAG application using LangGraph. For those of you who are not familiar, LangGraph is a library developed by LangChain that allows you to build complex AI applications represented as graphs. And a node in the graph does some unit of work, passes its outputs to other nodes it's connected to. And a node can be an LLM, a retriever, or some other custom function that you can define. And this way, LangGraph allows you to build more complex flows using conditionals and loops, which is very important for building reliable AI applications. And that's also very important in RAG applications too. So for our documents in the RAG application, we're going to be using documentation from Pandas. That's a very popular library for data analysis and structured data, and one of my favorite Python libraries as well. So first off, let's talk about what self-corrective means in this case. Consider a very simple RAG pipeline. Very vanilla. We just have a vector store and LLM. We take user's question, we retrieve relevant documents from the vector store, we pass those to LLM, put that in the context window, and then try to generate the answer based on that. There are at least several problems with this vanilla approach. First off, we can have issues at the document retrieval step with the document relevance. With irrelevant documents, we will not be able to generate a good answer. And then even if we did retrieve good documents, at the generation phase, there's a couple of other issues that we can encounter. One is hallucination, so LLM can just hallucinate an answer and ignore retrieved documents, or there could just be a completely irrelevant answer even if it is grounded in the documents. Consider another approach to sort of defining these flows where it's not entirely defined by the developer ahead of time, like in that simple vanilla RAG, but rather we have LLM as part of that control flow where LLM actually makes decisions on where to go next. So for example, I can inspect the outputs of the previous step in the execution and decide, should we redo it, or maybe everything is good and we continue our execution. And that's particularly important for RAG as well. So over the last couple of months, there's been a lot of different papers addressing that. So a couple of them were self-RAG and corrective RAG that dealt with different types of issues that I just described. We actually did videos on that already in terms of how to implement those papers using LangGraph, so definitely make sure to check those out. And here, what we're doing is taking ideas from both of those and particularly focusing on the sort of answer hallucination, answer quality phase of this rather than necessarily the document retrieval relevance. So again, what we're doing here is we take user's question, we retrieve a set of documents from the vector store, and we try and generate the candidate answer based on that. From here, things get interesting. First off, we're trying to check the answer for hallucinations. So if there are any hallucinations, we go back and try to regenerate the answer again. If there are no hallucinations, we do another check, which is, does the answer actually address original question? Is it a good quality answer? And if it's no, not relevant, we'll try and rewrite the question and do another document search. Then we'll redo all of those checks again, and if we pass those, that's great, and then we'll return the answer to the user. We try that for several times, and if we're still failing at the end, we're going to fall back in a very simple web search where we take the user's question, we retrieve a set of web search results, generate the answer based on that, and then just return that answer to the user. So before we proceed, I'd like to show you how this looks like in a final deployed state. So what we're going to be using for deployment is LangGraph Cloud. That's our one-click solution to deploy and host LangGraph applications. And let me show you how that's going to look like. So here you'll see LangGraph Studio for our application deployment. And LangGraph Studio allows you to visualize and interact with your graph, as well as debug its execution for different types of inputs. And I'm going to show you two queries here. First off, I'm going to show you a query where we're going to get good quality answer with no hallucinations based on the documents in the vector store. And the second query, we're going to try and ask the question about documents that are not even in the vector store. So we know for a fact the model will try to hallucinate. We're then going to regenerate the answer for one additional retry, and then if we fail, we're going to just fall back on the web search. So let's try the successful query first. So because we're working with Pandas, let's try a very simple query such as how can I calculate some bigroups. So you'll see what we're doing here. We're retrieving documents, generating candidate answer, and then since we passed all of the checks, we finalize the answer and return it to the user. So things look pretty good. Now contrast this with the query where we're going to have a hallucination. The reason for that is that there's no document in the vector store to answer this question. So the model will try and come up with the answer that's not based on documents. So let's ask, how can I convert a categorical column into dummies? And you'll note the first steps are pretty much the same. We retrieve the documents and we generate candidate answer, but then we actually fail at the hallucination grading and we need to regenerate the answer again. So you see it over here. And then because we did only one retry, we actually go to web search and then generate the answer again. And now we succeeded because we did get a relevant document from web search. So the answer that we're returning to the user is actually grounded in those search results. Now let's head back to the notebook and I'll actually show you how to build this step by step. Our LLM is going to be Claude by Anthropic. We're going to also use the Chroma database for vector store retrieval. We're going to use OpenAI embeddings also for storing the data in the vector database. We are also going to use Tavili search as our web search tool for the fallbacks. And we're also going to define Langsmith tracing for logging data to our production system for developers that allow us to monitor our LangGraph application and see different steps in more detail. So let's set up our environment. We'll install several dependencies and then we'll set our API keys, which I've already done here. We're also going to import a few things from various LangChain libraries, ranging from the integrations to just key primitives for vector store retrieval, for prompting, etc. And then we'll also import LangGraph, which is the most important part for building the LangGraph application. Then we're going to set up several key components such as model, retriever, and tools. For the retriever, we'll have to do several additional steps to format the data in the right way. As I mentioned, we're going to be working with the Pandas documentation, but you'll note that we're looking at a very small subset of it, specifically just 3 pages from user guides. The reason why it's so small is actually it's done on purpose because the library itself is very popular and there's a lot of information on the web already about how to use it, and all of this data was actually part of training data for LLMs. So the model already has a lot of Pandas knowledge encoded in the weights. So what we could end up with is if the model does not see the information in the retrieved documents, it might still try and generate the answer. Now, in some cases, it's actually nice and could be a useful fallback, but in other cases, it might not be desirable. And what we're going to show here is how to actually deal with those situations where the model still hallucinates the answer or like tries to come up with the answer, even though that answer is not grounded in the retrieved documents. So again, for retriever, what we're going to do is we're going to try and fetch data from those 3 source web pages. Then what we're going to do is prepare those documents, namely we'll chunk them up into smaller pieces for retrieval, and then we're going to index them into this Chroma in-memory database using the OpenAI embeddings for embedding the text. And then we'll create that retriever. We'll also initialize the LLM, which is in our case Anthropic most recent Claude 3.5 Sonnet model, and we're going to define Tavili search tool for doing the web search. Now we're getting to the key part in setting up any LangGraph application. We're going to define the graph state. So state is the core object for any LangGraph application because that's going to be representing the data that each node has access to and the object that each node is going to update as it's executing. So what we're going to keep track of here are a list of messages, because we want our app to be chat-based. So user inputs a human message and gets AI message with the final answer as the response. Then we're also going to keep track of the original question that the user asks, the documents that we retrieve at any sort of retrieval step, the candidate answer that we're going to be grading, number of retries. So that's basically just allows us to control, how many retries we've already done, so that we can go to the web search fallback, and then the actual indicator whether we're still allowed to do web search fallback or not at the end. And then we're also going to have the configuration for the graph that allows us to pass the maximum number of retries parameter at runtime, which will be quite handy. Now let's set up the graph nodes. The first one, quite obviously, is going to be the actual document search node. You'll note that each node implementation is going to be a function that takes the state object that we just defined, because it needs to read the information from state, and then it's going to return the update to the state. The update is usually going to look like a dictionary, where the key is going to correspond the key in the state, and the value is going to be the value of the actual update that needs to conform to the same serve type. And in the document search, it's going to be exactly what you would expect. We look at the list of messages and grab the most recent message from the user, which is the human message. We get the content of it, pass it to the retriever, and get the list of documents. Then we also update the question, and the web fallback is set to true, which means that so far we're allowed to do web search fallback if we exhaust the number of retries. That'll be relevant in just a little bit. Then we define our answer generation node. Here, what we're saying is we'll need the question and documents from the state. We're also going to look at how many retries we've done so far, because we would want to increment that. We're going to be incrementing this at the generation step. And then we're going to define the actual chain or sequence that's going to be responsible for answer generation. What we're doing here, we're basically saying we're going to take the LLM and we're going to call it with a specific prompt that we've pulled from LangChain Hub, which is a predefined set of prompts in this case. So for RAG, we already have that there. And then we are also going to grab the content of the last message from the LLM and just return it as a string. That's what the output parser does here. So we pass our context in question, get the generation, and return that to the state as a candidate answer. Note that all we need to return from the node is just the update. So we don't need to still return all of the keys at each step. We're only returning the updates that are relevant at this node. Then we're going to define the node that rewrites the original user question. This is useful if we see the answer being irrelevant. We go and rewrite the original question and try the whole loop again. That's where it's going to be relevant. So we grab the question here, and then we are going to do a similar definition of a query rewriter chain, where we take an LLM with the prompt and then parse the output into a string and simply invoke it with the question to rewrite. Then we're going to define the web search node. That's going to take the original user question and then invoke the search tool with that question. Then we're going to stitch the content from all of those search results into a single document, and we'll just mark it as a source web search for convenience. We're just going to add this document to the set of existing documents for simplicity. And we're going to say that once we've done web search, we no longer are allowed to do web search fallback anymore. So we're updating it here. And then finally, we're just going to take the graph state once we're ready to return to the user and just format the candidate answer into an AI message, because again, we want this to be structured as a set of chat messages for the chat application. Here we're getting to a quite interesting part where we are doing those checks on the answer hallucination and answer relevance. So we're defining the system prompts where we're asking the model to check whether the answer is grounded in the source documents, as well as whether the answer actually addresses the original question. And what we're also doing is we're defining these pydantic models, which will actually be used just a little bit lower in this notebook, where we're going to ask the LLM to return the output in the structured form. So these are just going to be used to parameterize the LLM call to always return a pedantic model instead of just a message or a string. And this is the key piece of our control flow logic. It's going to be a conditional edge that I'll cover in just a little bit, but effectively this is a function that says, given the state, where should I go next based on a set of conditions. So unlike the node implementation where each function takes the state and returns update to the state, the conditional edge here will take the state and return the name of the node where you should go next to based on satisfying certain conditions. So we're going to look at the question, document, and candidate answer generation so far. We'll check if we're still allowed to do web search fallback, keep track of retries, and also we're gonna grab the maximum number of retries from the config. So you see we're also passing config in addition to the state in this function. You can actually do that in node implementation as well. So let's look at the key pieces of logic here. We're going to be grading the answer for hallucination. You'll see that the LLM configuration takes the pedantic model that we defined earlier, and we just need to call the LLM with structured output. This is going to ensure that we're going to get the output as pedantic model. And then we're going to invoke that with the set of documents we retrieved as well as the candidate answer generation. That's what the prompt here is expecting. Then if we're going to say if the grade is no, meaning the answer is not grounded in the documents and there is a hallucination, we'll either try to generate the answer again, if we're still allowed to do that based on the number of retries, or we'll just go to web search fallback if we're not. If we don't have any hallucinations, we actually get to the next stage, which is the grader of answer relevance. So we're going to similarly invoke the LLM with the structured output, ensuring that we return a pedantic model, and we'll say if the answer is addressing the question and is relevant, we're going to just finalize and return to the user, and if it's not, we're going to try and rewrite the query. Again, ensuring that we're still allowed to do that based on the retries, and if not, we're going to go and fall back on web search. Lastly, there was this piece of logic here. All it's doing is just saying if we are no longer allowed to do web search fallback, which would happen after we do the web search fallback, we'll just go to the finalized answer and return to the user. Now let's assemble the graph. So we've done all of our node definitions and we can add them here. First off, we define the state graph object that takes the schema of the state, which is the graph state, as well as the schema of the config, which has the max number of retries as the only parameter. We'll add all of our nodes, which is going to add the name and then the function that corresponds to the node. Then we're going to set the entry point. That's where our graph execution is going to start. In this case, it's going to be document search as the first node. So take the question and do the search first. And then we'll define a bunch of edges. We're going to define both regular edges and conditional edges. So regular edge is basically just saying you have to go from A to B. So once you're done executing node A, you're just going sequentially to node B. Conditional edge is saying from node A, you can go to a bunch of other nodes depending on satisfying certain conditions. And this function is what's going to determine how you're supposed to do that. So that's exactly what we just looked at in this grade generation function. And this is why we're returning the names of the nodes here. It's because it's telling the graph that that's where you should go next. Lastly, we have to compile the graph so that we can actually use that as runnable. You can also visualize the graph, and this visual corresponds very closely to the original flow we defined. It just looks slightly different because it's auto-generated, and we can actually run the graph. One thing that LangGraph is particularly well suited for and has first-class support for is streaming. So in particular, we can stream the full values of the state after each step in execution of the graph, or we can also stream the updates instead of the full state, and we can even stream the individual tokens from LLMs inside the graph nodes if we wish to do so. But first, let's try and stream the outputs from the graph. Here I'm just going to print out the printouts from each node saying what's happening so you can see it step by step. I'm going to ask a very simple question: how do I calculate sum by groups? It's a very vanilla Pandas operation, and it's actually covered in our underlying documents that we indexed. So let's run this, and you'll see that we're retrieving document, we're generating the answer, checking hallucinations, and we pass that filter. We also pass the check for the answer relevant, and we're ready to finalize response. Here I just printed out the outputs from the nodes, but you'll see that the full sort of state update outputs will look like this. Get the output from the document search node with the question, documents, and some other information. Then we'll get the output from the generate node with the candidate answer. And because the answer actually passed all of the checks, we'll get to the finalized response, and we get AI message with the content here. And if we'd like to stream the underlying tokens from the LLM, we'll see that these are the individual tokens from candidate answer generation as it's coming out of the LLM. We're also getting some partial tool call information. The reason you see tool calls is because that's what's powering our Pydantic model structured output parsing under the hood. And that's basically it for a simple streaming demo. Now, let's try a query that would require web search fallback. This query is for the information that's not contained in the index documents. That's where we're actually going to trigger that hallucination behavior. So you'll see we're retrieving the document, we're generating the answer, and we're not passing the first check, which is the hallucination check. We do one more try because we've set max retries with the configuration here. And after that, we're doing the web search fallback. And once again, we're generating the answer, and now we're just finalizing the response to the user. So that's how you can also implement the check and do a web search fallback. The other piece of LangGraph functionality that's incredibly useful for these kinds of workflows is persistence, and that's what enables you to do things like human in the loop. So persistence basically just gives your graph memory, and you can create different types of memory here. The simplest one is just in memory. That's what we're going to use, and you just compile the graph differently, with passing this checkpointer or memory object. We're going to create a thread configuration here that's just saying that this is going to be our current graph execution history. If you want to start a different one, you'll just create a new thread. And let's try a question again where we had the hallucination before. So you'll see we run the same steps. We get some documents here, but we actually stop before generation step. So that's because we specified this interrupt before and the name of the node where we want to stop. So we stop before the generate node. What we can do next is actually help the model a little bit, because we know for a fact none of those documents that we indexed contain the right information to answer this. We can actually inject this information on the fly. So we can take the list of documents that we retrieved, and we can just override the content of the first document to contain the right answer, saying to convert a column into dummies, use this method. So we're going to do that, and we're going to call update state, which is for that specific thread in memory. We're going to update the documents value, and after that, we can continue streaming from the interrupt point and see what happens now. So note that when we're doing this, we're also passing empty inputs. And you see that here we got to generation step, we produced the candidate answer, and we passed the checks. We immediately got to finalize response. So we didn't have to do any retries, we didn't need to do a web search fallback. And now I'd like to show you the same thing, but in a deployed version on LangGraph Cloud. LangGraph Cloud is our one-click solution to deploy and host LangGraph applications. First off, I'd like to show you how implementation of the same app would look like in sort of LangGraph Cloud friendly specification. So let's head over to Visual Studio, and you'll see that agent file will contain exactly the same logic that I just described. It defines all of the necessary components. It has all of the necessary prompt and grading logic. We have our graph state. We have our graph configuration. We have all of our nodes and edges. And we define the graph workflow exactly the same way. And the key piece here is that you need to have the variable with the compiled graph. That's what we're going to be looking for when trying to deploy the LangGraph application on LangGraph Cloud. And the second piece you'll need is the LangGraph JSON configuration. You can specify multiple things here. The key one is pointing the LangGraph deployment to the right list of graphs to work with. You can specify multiple ones here, but we're just going to do one. We'll call it agent, and we're going to point it to the right Python file and to the variable that contains the compiled graph. That's very important. Then you can also specify dependencies to install. I'm just saying I want to install dependencies from the current working directory, and it's going to look for PyProject or requirements file. In this case, we have a bunch of requirements specified in Poetry PyProject file. So we're going to do that. And then you can also specify additional things like environment variables or files containing environment variables, etc. This is all you need. And then you just need to also put all of this into a GitHub repository that contains exactly the same structure. So LangGraph JSON file and the agent implementation or multiple implementations if you need. And then you'll head over to Langsmith. Specifically, we'll go to deployments page. And if you wish to create a new deployment, all you're doing is specifying the repo you'd like, the name for your deployment, the configuration file that you need, and then you can even define your own environment variables here, and then you'll be good to go. But I'm going to show you the deployment that already exists for exactly the same application I just showed you here. So when you open that, you'll see that you have a list of revisions. So every time you deploy, you'll see a bunch of revisions reflected here. You'll also get traces, similar to how you would normally see traces when you're working with Langsmith. So that allows you to actually go ahead and inspect a particular LangGraph execution. You can see all of the steps here again, like document search, generation, all of our gradings in between, and so on. And you can actually interact with the graph here through the deployment using LangGraph Studio. This is our interactive UI where you can do the same runs that I just demonstrated in a notebook, but in sort of more user-friendly way. So you see exactly the same graph structure, graph architecture that I outlined earlier, and you can sort of start a new graph run by first specifying some inputs and then submitting them. So let's try the same question, which is how do I calculate sum by groups? So we'll run that. And you'll see that we're getting the outputs live as the graph is streaming. So we get document search results. We get a bunch of documents retrieved here, and we can inspect further if we want to. We see the candidate answer generated. We didn't need any retries, so we got immediately the finalizing answer, and we got our AI message here at the end. So that's a pretty simple workflow. Now let's try something else. Let's try the query that was failing, namely how do I convert a categorical column into dummies. What we're also going to do is to mirror that interruption in the notebook, we're going to add an interrupt here. Now when I run this, you'll note that I stopped here, and the graph knows the next node to go to is going to be generation node. But before we do that, we also want to try and edit it here, similarly how we did this in a notebook. So I'm just going to copy this answer from here for convenience. And I'm going to just completely replace this document content over here. Now, what we're going to do in the UI is we're going to create a new fork. So that's going to create an alternative execution from that point on, from the interrupt point. And you see that what we're doing here is we're generating the answer, which is the candidate answer. We're doing some grading for hallucinations. And you see that instead of going to generate again, which would happen because of the hallucinations, we didn't have any. Therefore, we're going to straight to finalize answer and return to the user. So you see that we helped by injecting this information over here. So that's a quick demo also of how you can deploy and reproduce the same behavior that we showed in the notebook for self-corrective RAG, but using LangGraph Cloud. And that's all for today. Thank you so much for watching. Hope you've enjoyed that. And let us know if you have any questions or suggestions below in the comments. And hope to see you in the next one. Bye.